Okay, so I'll come back. Now we are going to continue from when n is equal to 1. We're given a function f of x, and we're asked to prove that the function f of x admit on dl, and we're given orders where we're supposed to reach to prove that the function admit on dl. Now we write back f of x is equal to 1 plus x plus 2x squared plus x raised to the power of 3. So for when n is equal to 1, we apply the same principle. We know f of x, the formula, the polynomial formula and the rest. We have a0 plus a1 of x plus a2 of x squared up to an of xn. So in this case, we are taking an of xn with n equal to 1. So if n is equal to 1, that means this will be 1 and this will be 1. And so we'll be left with a1 x 1. And you know, anything x raised to the power of 1, it's itself. So we are left with a1 x. And a1x, like I said in the last video, there is a certain constant here. In this case it's 1, so that 1 times x will give us x, and so this is our a1 and then this is x. So yes, this function admit on dl because we've been able to verify the condition. The thing that will be left is for us to verify the rest, which is epsilon of x. That's epsilon of x. Now, so we have, in this case, we have a0 plus a1 of x. So that means we have 1 plus x. So we'll write that down. So just clean this part. Remember, if you have any question based on this video, you can always put it in the comments below, and I'll be available to answer your questions if there's anything you don't understand. So we said we'll write what we've gotten. So f of x will be equal to 1 plus x, which is a0 plus a1 of x. So 1 plus x, and whatever is left is our epsilon of x. Now in this case, now let's take notice of this. We know it's an epsilon of x. In this case, our n is equal to 1, so that means we are left with x epsilon of x. And after bringing out 1 plus x, our rest 2x squared plus x raised to the power of 3. Now the rest that we have now, we have 2x squared plus x raised to the power of 3. But remember that we have x right here. See this? Okay, so remember we have x right there, and so we have to factor out an x from this expression so that we'll be able to get our x epsilon of x. In the previous one, we did not do that because it was x raised to the power of 0, and remember when we said anything raised to the power of 0 is just going to give us 1. So in this case, we'll factor out x so that we'll be able to have x epsilon of x. So great, let's do that. So if I factor out x from here, we'll be left with 2x plus x raised to the power of 2. So we'll be left with 2x plus x raised to the power of 2. Because if you multiply this x again, you get 2x raised to the power of 2 plus x raised to the power of 3. So that means our epsilon of x, the exact epsilon of x we have, is this 2x plus x raised to the power of 2. So we'll write that down. Just leave this for now. So x epsilon of x. Okay, so where the limit when x tends 0, okay, sorry about that, when the limit when x tends 0 of 2x plus x squared, because remember we factored out x, 2x plus x squared will give us 0, because if you apply the same method, the limit when x tends, that means where we have x, we replace it with 0. So we're having 2 0 plus 0 square, and 2 times 0 is 0 plus 0, so 0 plus 0 will give us 0. So the limit is 0, and yes, it verifies the condition that says that the rest has to tend 0, that the rest has to be equal to 0 when x approaches 0. So this is bien défini. Like, we've been able to prove the second part. I'm so sorry about the small board, but we'll try our best. So x tends 0. Just write this nicely again. Okay, so we've been able to verify for when n is equal to 1. Now for when n is equal to 2, the same principle apply here again. So like the formula for development limit, like I always say, it's always cool if you actually write it down in your record book so you don't get to forget it, or when you just want to go through your revision, you don't have to go back to your lecture and then start checking where exactly is the polynomial and the rest. So for when n is equal to 2, it means we do this again. So n is equal to 2, so that means we are going to have a2 x2, and yeah, right here we can find x raised to the power of 2. So that means our a2 is equal to 2, so that we can have 2x raised to the power of 2. So bien, we have a0 plus a1 of x as well as a2 of x squared. So that means this function also verifies the polynomial part of our formula of our DL. So that means for when n is equal to 2, our f of x will now be 1 plus x plus 2x squared, because for n equal to 2, we replaced here with 2 and we replaced here as well with 2. So that means for when n is equal to 2, f of x will be equal to 1 plus x plus 2x squared. Now again, we'll talk about the rest. So you see, it's a step-by-step process. And alright, so again, for the rest, we know it's x raised to the power of n epsilon of x, and in this case our n is equal to 2, so that means here our n will be equal to 2. So that means we have x raised to the power of 2 epsilon of x. And from here, remember, after bringing out this part of the function, we're left with x raised to the power of 3. So how can we get our epsilon of x? Remember, we have x raised to the power of 2 already. So, and if we have x raised to the power of 3, it means, and we have to factor out x raised to the power of 2, so we can get our epsilon of x, because n is equal to 2. And we are left with just x raised to the power of 3, and we have to get our epsilon of x. So if we factor out x raised to the power of 2 from here, we'll be left with x. And so our epsilon of x is just x. So write that down. Okay. So plus x raised to the power of 2 epsilon of x, ou la limite lorsque x tend vers 0 of x is going to be 0, because if x is equal to 0, automatically this will be 0, and so the limit of a constant, when you're calculating the limit of a constant is itself. So the limit, because here we'll be left with 0, and so 0 will automatically get 0 again. So yes, this function also admit on DL because it verifies the polynomial part, which is this part, and then our rest. So now for when n is equal to 3, we apply the same method. So I'll take this out. So for when n is equal to 3, the same thing, we apply the same method. So we have f of x will be equal to an x raised to the power of n, right? So n is equal to 3, so we have a3 x raised to the power of 3, and so we see x raised to the power of 3. Oh, this, okay. Okay. Ninja. Okay, so x raised to the power of 3, x raised to the power of 3 is, we have it here already. So, and a3 here is 1, so that means we have a3x of 3 already. So that means we have a0 plus a1 of x plus a2 of x square, there's a square here, and then plus a3 of x 3. So that means our f of x will be equal to 1 plus x plus 2x squared plus x raised to the power of 3. So we'll write that down. Again, we are going to look at our rest. So we said our rest is x raised to the power of n epsilon of x. Now our n is equal to 3, and so we have x raised to the power of 3 epsilon of x. Now in this case, how can you get your epsilon of x? In those other cases, we were able to factor out x in order to get our epsilon of x, right? Here we have x raised to the power of 3, which is our last order, and so what's going to happen is we'll find out if our epsilon of x, okay, first let's write this down. So x raised to the power of 3 epsilon of x. Just do this so we'll have enough space. Alright, So here also, if you look, you notice that since x raised to the power of 3 is just there, it means that epsilon of x is equal to 0. And so in this case as well, we are going to have our epsilon of x equal to 0 so that we can have this limit. So the limit of epsilon of x when x tends 0 will give us 0. And so this function also admet bien un dl à l'ordre 3. So finally, we are looking at for when n is equal to 4, is greater than or equal to 4 au voisinage de 0. So when n is equal to 4, n greater than or equal to 4, so when n is greater than or equal to 4, it means our x raised to the power of n epsilon of x, n will be 4, and then we have epsilon of x. Again, now the thing is here, now the thing here is we have up to the order of 3. Okay, so I just want us to listen to this and watch this closely. We have up to x raised to the power of 3, but now they're asking us for x raised to the power of 4 and x raised to the power of 4, x raised to the power of 5, up to x raised to the power of n, because we're having this condition, n greater than or equal to 4. So in this case, what we do is f of x would be equal to 1 plus x plus 2x squared plus x raised to the power of 3. Now, because we have to go from the order of 4 up to the order of n, and we don't have any constants in those cases, like, so that means since we don't have constants in those cases, it means that from our a4 x raised to the power of 4 up to our an x raised to the power of n, it means our constant probably not like our constant has to be 0 in each case, so that this whole thing will be out and then we'll be left with just this function. That's basically what it's talking about. So from our a4 will be 0, our a5 will be 0, up to our an would be 0. So we can have this function again. So à l'ordre 4, we have 0x raised to the power of 4. À l'ordre 5, we have 0x raised to the power of 5. So in conclusion, it means if you are given an order, let me say to the order of 4 in this example, and you know you don't have anything for the order of 4, you either replace it with 0 or you skip it and then just write what the next term will be, or write basically what the rest will be. So in this case, it will just be 1 plus x plus 2x squared plus x3. But because we don't have, if that were asked to just go to the order of 4 and not n greater than or equal to 4, and not n greater than or equal to 4, if it was just n equal to 4, then it's either you write 0x raised to the power of 4, or you just leave it, and because this will just give you 0. I remember we're in addition, so it won't really make any difference. So you just have this plus the 0x raised to the power of 4 and plus your rest. So we already understand that we are going to the order of 4, but we don't have the order of 4 in our function. So we just write that it's in our rest, and that why we don't have order of 4 is because there's 0 in our constant. So if we continue this, we'll go up to 0x raised to the power of n plus x raised to the power of n epsilon of x. You can see that. So x raised to the power of n epsilon of x. And if we add 0 plus 0 plus 0, 0 plus 0, 0 plus 0, we'll keep getting 0. So we are left again with just 1 plus x plus 2x squared plus x raised to the power of 3. And so in all the cases from when n equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 4, realize that they all admit on dl overznash the 0. So in our next video we'll try out another example almost similar to this. So thank you for watching and see you in the next video.